Hey everyone, I'm Taylor. I work on Rust and C++ Interop at Google.
Hi, I'm Tyler. I co-lead the Rust language design team, and I also work at Google. Taylor and I are so excited to announce here on stage for the very first time that
Contrary to popular belief,
we're
not the same person.
Anyway, we're at RustConf, so let's talk about Rust. Rust is a systems programming language.
No, stop. We're at RustConf. Everyone here already knows that Rust provides memory safety, fearless concurrency, and has been voted Stack Overflow users' most loved language 9 years in a row. Rust evangelism strike force, Tyler, really? All right, let's talk about C++. According to the TIOBE index, C++ is the second most used language only after Python. Despite growing calls for modern memory-safe programming languages, developers are still writing nearly 20 times as much C and C++ code as Rust code. The popularity of C and C++, combined with their long history of usage throughout the systems programming world, means that an overwhelming proportion of large existing code bases and APIs are expressed in C and C++.
But if you're an advocate of memory safety, don't despair. The good news is that even if your code base is mostly C++, you don't have to rewrite it all to make substantial gains in memory safety and reliability. So most bugs and vulnerabilities arise in new code, and they decay exponentially with time after that. This is actually well supported in research. So you heard me. You don't have to rewrite it all in Rust. You can actually achieve a major reduction in bugs and vulnerabilities by using Rust to implement new features. But that can be hard to do. It isn't as easy as choosing to write a .rs instead of a .cc file. The new Rust code, it's going to have to call back into C++, and then that C++ is going to have to call back into the Rust.
This is a problem even for code bases which do want to migrate to 100% Rust. For even a moderately sized project, it won't be feasible to convert everything to Rust all at once. So there will be a period of time during the migration where C++ and Rust code have to interact. For example, the fish shell recently completed its migration from C++ to Rust. They were having a rough time using C++ due to its inconsistent tooling and platform support, poor ergonomics, threading hazards, and a disjoint community. They were excited to use Rust. It's cool, it's fun, it provides great tooling and an excellent community. So they set out to port fish from C++ to Rust. In order to accomplish this port, they needed to migrate components one by one from C++ over to Rust. They described this gradual migration as a necessity. Without a gradual migration, they wouldn't have had a working program for months, they might not have finished at all, and they would have had to redo a bunch of work once the project became testable after conversion. However, this plan hit a snag. Rust and C++ interop. Today, the situation is messy and the tooling is limited in what it can handle. In the end, they managed to pull off the conversion thanks to some developer heroics, porting modules sometimes as large as 13,000 lines of code all at once. These developers were determined to see it through the transition, and they didn't have a boss hovering over their shoulder during the port, bugging them about when it was going to be done. Not every project has that luxury.
Most projects don't, which means if they want to use Rust, they're kind of stuck. Now, let's remember that Rust has a history of empowering developers along many frontiers, making it easy to do what was previously hard. So first, Rust began to excel at CLI tools, and then it was high-performance web servers and databases. Then Rust was reaching into satellites and space and embedded microprocessors. And now Rust is even in the Linux kernel, which runs on billions of devices every day and includes some of the most hardcore systems programming there is. These are all places where C and C++ have excelled, but if there's one thing in this picture that Rust does not play well with today, it's C++. Rust and C++ simply share too many of the same spaces to stay air-gapped forever. But Rust is still very much a growing ecosystem with an evolving language. If we could tackle all of these challenges, we could certainly take on C++ interop. I'm feeling optimistic. Are you, Taylor?
I'm feeling okay.
All right, I'll take it. Let's cover what we're going to talk about today. First, we're going to talk about what works, which is the state of Interop as it exists today. Then we'll cover where the gaps are, the places where it kind of falls apart. This will come with a call for a better Rust. How can we make Rust better for Interop and for the benefit of all Rustaceans? Let's dive in.
There are a number of tools in the C++ Rust interop space already today. Let's take a look and understand what they do well and what's still missing. Bindgen is the most widely used tool in this space. Bindgen takes in C headers and outputs Rust FFI bindings, allowing Rust to call into existing C APIs. C bindgen does the inverse, allowing C code to call into Rust APIs.
Bindgen and cbindgen both make use of source generation and build integration. This is a common theme we'll see in many of the tools that we will talk about. These are both examples of extension points that go beyond what the language can do natively.
However, both of these are low-level tools which only allow working with C API-compatible functions. This means that APIs must all consist of simple C-style structs with public fields. If we want to use types from the Rust or C++ standard library, normal user-defined data types, we're out of luck. That means no classes, no Rust enums, no RAI types like box, unique pointer, or string, and definitely no user-defined generic or templated types. Today, we can't even pass around slices since their representation isn't guaranteed. In practice, this means that FFI code requires a lot of manual, unsafe, and error-prone work to convert in and out of C-based representations, as well as separate declarations of RAI-based types. This brings us to CXX, a bindings generator that offers solutions to many of these problems.
CXX takes a different approach from bindgen and cbindgen. So rather than reading from header files, the user declares their shared C++ and Rust APIs in an FFI module, which is annotated with the CXX bridge macro. That module is then used to generate the resulting Rust API and a C++ header. That allows users to declare these safer, higher-level interfaces that make use of standard types like slices, vector, unique pointer, and string. There are some limitations, though. You have to manually rewrite your item declarations inside of the FFI module. That's because CXX can't see into the definition of pre-existing types, either in Rust or in C++. And since CXX doesn't know the memory layout of the existing types, they can't be passed around by value. So they require an indirection through a box or a unique pointer. To solve that issue, let's have a look at Zungar.
Zengar is another newer tool in the interop space. Similar to CXX, Zengar relies on users manually declaring their C++ and Rust APIs in a custom interface definition language, or IDL. Unlike CXX, however, Zengar allows users to specify the size and alignment of their types so that they can be passed by value over function boundaries without additional heap allocation or indirection. However, requiring APIs to be redeclared in a separate .zng file makes it hard to use Zengar with large existing API surfaces. Crubit is a new ongoing project at Google with the goal of making every non-templated C++ function callable from Rust, and vice versa. Crubit takes advantage of native compiler integration with both Clang and Rust-C in order to provide maximum coverage of existing APIs. However, this approach has some limitations. Not all users of C++ interop can use Clang, and some of them need to work with multiple toolchains. In these cases, IDL-based approaches like the ones used by Zengar can be a better fit.
So within the realm of C++ interop, no two projects want exactly the same thing. Some projects want auto-generated bindings for every API, while others want to manually pick and choose which APIs get bindings. One might depend on unstable details of the toolchain for better ergonomics or even safety, while another needs to work across many different toolchains. One user might be tied to a fixed C++ ABI, while another uses an unstable ABI and rebuilds everything from source. So can there ever really be one interop solution to rule them all? I mean, how could it even begin to handle this amount of variation? One idea is through the use of IDLs, or interface description languages, like the ones we saw with CXX and Zungar. An advantage that IDLs have is that the author can control how many details of an API to include. So for example, Zungar allows users to choose whether or not to specify the size and alignment of a type. If that information is there, you can pass around that type by value. If not, it's usable, but only behind a pointer. In return, though, you don't have to update your bindings every time you change the type's layout. And so it'll be more robust, and it won't be tied to a particular C++ or Rust compiler. There may be a way that we can use IDLs that also allow for easy use of these large existing APIs, which is to have tools auto-generate our IDL for us.
Today, Crubit takes in header files and then directly produces Rust APIs. But in the future, the plan is for Crubit to produce a customizable IDL, which can then be transformed into Rust code. This will allow users to take advantage of the IDL to Rust translation, regardless of whether or not they use Crubit's Clang integration.
These tools all represent excellent steps forward, and it is possible today to create a mixed C++ Rust codebase, particularly if you have small API boundaries that don't change frequently. But all of these tools suffer from similar problems because of C++ features that just don't map onto Rust very well. You see, C++ is this immensely powerful and expressive language with a wide range of usage patterns, many of which are not easily expressed in Rust. It has many built-in extension points to support those patterns. Some of those extension points I consider mistakes in language design that don't belong in Rust. Our goal obviously should not be to turn Rust into C++. We can use strategies at the source generation layer to recover some of the usability of APIs that make use of these features. But let's also keep in mind that this level of flexibility has largely been responsible for C++'s success. Don't get me wrong, it's far from a perfect language, but the language has enabled people to write very high-performance systems code that felt far more expressive than anything they could write before. In this regard, there are some places that Rust can continue to learn from C++.
One area where we need to be especially careful is unsafe. Dealing with unsafety in C++ APIs is spicy. Who can tell me whether this API is safe for Rust to call? Anyone? Feel free to shout it out. All right, well, without seeing the C++ implementation, this is kind of impossible. You could call it unsafe always, but we can't really tell what the implementation is, right? While this example might seem silly, it's common for C++ APIs to document preconditions which have to be upheld in order to avoid undefined behavior. The obvious option then is to mark every C++ function as unsafe in Rust. But this creates a huge problem. When all your code says unsafe, it stops meaning anything. If we force developers to write unsafe around every call to C++, like the boy who cried wolf, the compiler's warnings to exercise extreme caution just lose their impact over time. Code reviewers also can't tell what changes they actually should be paying attention to and which things are like, an extra special unsafe transmute. This problem was so bad that the Fish developers actually forked their own version of AutoCXS just to turn off unsafe entirely. One option is to support C++ side annotations to mark a function as safe. This is a really great solution, actually. It allows C++ API authors to carefully analyze once whether a function is safe or unsafe to call. Callers then know what contract the API provides and don't have to litter every separate call site with unsafe, oh, this is okay. However, this also requires that the developers of the C++ API are aware of and willing to include safety annotations. This isn't always an option, such as when you're working with a third-party C++ library or a highly used C++ library whose developers don't want to see their function signatures covered in Rust-specific annotations. Another option we can use is type-based heuristics. For APIs that don't provide annotations, Interop tools can guess at whether the function signature is safe or unsafe. This approach is currently used in Crubit along with annotations. For example, if we see a function like the one above, we can guess that it's probably less interesting than a function like this. This analysis is obviously imperfect, unfortunately, because as we saw before, the first function can have some precondition that is required in order to uphold memory safety. However, I'm advocating for a harm reduction approach. By making functions like do something into safe C++ usage sites, we can focus our review efforts on mixed Rust C++ code bases on more dangerous APIs, which deserve a spiky unsafe. Raw pointers are the most obviously unsafe construct, but what about C++ references? Can the function above be safely callable from Rust? It looks kind of safe at first glance, but there are two big things differentiating this function from the corresponding Rust API. Does anyone have guesses? Feel free to shout them out. Yeah, exactly. So one of the issues is lifetimes. The Rust API assumes that the reference to the counter is only alive for the duration of the function call. But the Rust declaration also requires that the pointer to the counter doesn't alias with any other pointers. That is, for the duration of the increment function, no other code can read to or write from the counter. Let's talk about the lifetime issue first, since it's actually the simpler one to handle. As with unsafe, we can often kind of guess based on the function signature, and we can provide a system for annotating ambiguous cases. For example, we can assume that the mutable reference in our increment function is only valid for the lifetime of our function call. This inference can be wrong in some cases. For example, the constructor above stores a reference, which is still held after the function call ends. However, this practice is widely discouraged by C++ guidelines, as it can easily lead to hidden references to expired temporary values. In the case above, type with refs constructor saves a reference to the std string argument, but that std string, which is a temporary implicitly constructed at the call site below, will no longer be valid when the call to dot value happens. C++, the lovely language that it is, gives us the old as you wish and causes use after free and nasal demons. So to avoid this, APIs which store references beyond the lifetime of the function call conventionally take a pointer argument rather than a reference. Similarly, we can infer based on standard C++ conventions that methods borrow the method receiver only for the duration of the call, except when the returned type is reference-like, such as a reference, a pointer, a string view, or a span. Reference aliasing, on the other hand, as several people brought up, is a trickier problem. Rust's mutable references are guaranteed to be exclusive. They cannot alias with any other pointer in the program. C++ doesn't have this requirement. Mutable pointers can alias with other pointers. This has real effects on Rust optimizations. In Rust, we can safely reorder the load and store to the counter value to be before or after the call to the SomeOtherThing function, because we know that SomeOtherThing can't read or change the value of our counter. Our reference to the counter is exclusive. This optimization isn't valid on C++ code, where SomeOtherThing could read or write from the counter. This is a huge issue for gradual C++ to Rust migration. If C++ code uses multiple aliasing references, porting the implementation of a single function into Rust without making any behavior changes can introduce new undefined behavior. This is terrible. Rust, you were supposed to destroy the undefined behavior, not join it.
We'll talk about how to avoid this situation, but first let's talk through an example of how it can happen in the first place. Pure Rust prevents the creation of mutably aliasing references, so if we do have aliasing references, they must originate from C++. This can happen, for example, if a C++ field or a method exposes mutable references to Rust. So, for example, consider the CPP type API, which returns a non-const C++ reference from the getS method. This looks like a mutable accessor method, so we might expect to bind it like you would normally bind one of those, write one of those in Rust. What this Rust method signature says is that if the caller can prove it has exclusive access to an instance of CPP type, we can give it exclusive access to the value of S via a mutable reference. But when we peel back the covers of it, we humans can actually see that S refers to data outside the CPP type. Again, C++ references are not exclusive, so we have no idea where that reference came from or what other code is using it. That means on the Rust side, we've written a check that we cannot cache. Returning a mutable reference to Rust callers would be incorrect. And like we saw before, it would allow optimizations that change program behavior. So the first question is, what type should getS return instead? We know we can't use a Rust mutable reference. We also want it to be the same type that gets used when we see a C++ reference in argument position. That way, Rust callers can take the value returned by getS and pass it to takeS.
There are a few different options we can use to replace reference types: raw pointers, shared references with interior mutability, or custom C++ reference types. The simplest and most obviously sound option is to use pointer-based APIs for all references coming from C++. Using pointer-based APIs would force all C++ reference or pointer-using functions to be unsafe. Notably, this includes all methods, since methods take a reference to the method receiver, also known as this. This isn't a satisfying solution, as folks would be forced to throw around unsafe, raw pointers, and universal function call syntax in order to get their code compiling. One other interesting option is to use Rust's cell type. Cell is a transparent wrapper, which allows for mutation through shared references. This prevents undesirable aliasing-based optimizations we discussed earlier. However, Cell's API relies on some invariants that aren't upheld by C++ references. For one, Cell assumes that mutation can't invalidate other existing references. Although it's okay to project Cell through structural or product types like structs and arrays, it isn't okay to project a cell through variant or sum types like option. The reason for this is that changing the outer option to none will invalidate our reference to the inner type. You can see this above. If projection allows us to create a cell-wrapped reference to the I32 inside an option, that reference will be invalid when the option is set to none. The same is true of container types like vec or box. Modifying the container can invalidate references to its innards. Unfortunately, C++ provides reference projection functions for all of these types. This is the source of classic C++ problems like iterator invalidation, use after free, and more. As a result, C++ references mutating a type must be an unsafe operation. It can invalidate in existing references. There's one other issue with using cell for a C++ reference: threads. Because cell isn't sync, cell assumes that the object can only be accessed from one thread. But when working with thread-safe C++ APIs, such as a std atomic of bool, cell's APIs, such as get or replace, will read from the object without performing the necessary atomic load, resulting in undefined behavior. In order to properly handle thread-safe C++ types, all reads and writes must go through the public functions of their C++ API. One exciting alternative is to add a C++ style reference type to Rust. This approach avoids the instant undefined behavior that arises from aliasing Rust references. However, unlike regular Rust references, the C++ reference types do not require exclusivity in order to mutate. As a result, we've lost Rust guarantees that no concurrent mutation will occur. As we saw with cell and option, combining aliasing and mutation can result in data races, iterator invalidation, and more. Therefore, it must be unsafe to mutate through a C++ mutable reference where that mutation can invalidate an existing reference. The caller has to make this guarantee so that we know that the mutation isn't going to invalidate any existing references.
The Rust language today also has some missing features that make custom reference types like CPP-ref difficult to use. So one of these is field projection. When using an aliasing reference to a struct, we'd like to turn it into an aliasing reference to a field. With references, this just works, like in this example. But today, custom reference types require all this extra machinery, like the approach that pinproject takes, which is based on derives. We should add a generalized projection feature that works for all reference types, including custom ones. This would also improve ergonomics for raw pointers and for references to special types like maybe uninit and cell. Another feature is auto-referencing, which is a really nice ergonomics feature of method calls in Rust. So when resolving a method call, the compiler will automatically insert shared or mutable references to the self type when it looks for methods for a matching signature. This becomes so natural to use that you probably don't even think about it. Sadly, it doesn't work for custom reference types. If we have, let's say we have an own value of some type, we'd like to be able to easily invoke methods which take self as a C++ reference. Sadly, this code doesn't compile today. In order for our method call to resolve, we need the compiler to apply auto-referencing rules for our C++ references. Other library types like pin also want this ability. Field projection and autoref are examples of generalizing what already works in Rust to make it work for more use cases. We can take the principled mechanics that make Rust the language it is today and apply it to adjacent spaces, which would expand Rust's capacity to hold both the principled and the practical at the same time.
We've looked at 3 ways of handling C++'s potentially aliasing references in Rust: raw pointers, interior mutability with cell, and custom C++ reference types. None of these approaches are perfect, but with some help from the Rust compiler, we can begin to offer safer and more ergonomic APIs. Let's talk about movability, another big issue with C++. Rust expects that all types can be relocated with a simple memcopy. Common libraries like vec of t rely on this behavior, and this assumption has been heavily baked into unsafe code throughout the Rust ecosystem. Rather than calling a move constructor, unsafe Rust code has always been allowed to simply bitwise copy values to a new location. C++, on the other hand, makes the exact opposite assumption. Nearly all types in C++ require running code in order to relocate them. These relocation functions, called move constructors, commonly perform some work to fix up the moved value. Frequently, this is due to types that are self-referential, where one field contains a pointer to another, neighboring field. When the object is moved, the pointer needs to be updated to point to the new location. For example, the libstd C++ implementation of string stores a pointer to the string data. Usually, this data is heap allocated, but for small strings, the string data gets stored inside the string itself. Rather than introducing a branch on whether the data is inline or not, the string sets the data pointer to point directly into the inline string data. This means that, like other self-referential types, std string in C++ can't be relocated via a simple Rust-style memcopy. Thankfully, there's growing support for using Rust's pin type to represent values that can't be memcopy relocated. Immovable, in-place constructed, and move constructible values are super useful, even in native Rust. However, there's still a lot of work to be done before working with these values is ergonomic. All the issues we discussed before with aliasing references around field projection, reborrowing, auto-referencing, and method calls still apply.
A final crucial item missing from the interop story is calling overloaded functions. Many C++ APIs make use of overloading, and users need access to those APIs. A second reason overloading is so important to interop is because maintainers of C++ APIs assume that they can add function overloads without breaking their existing users. If having Rust customers means they can't evolve their APIs in this way, they simply won't want to have Rust customers. And this is true for every language with overloading, of which there are many. Rust has long avoided function overloading for a couple of reasons. For one, it can make it hard for developers to determine which function is actually called. Another reason is that it weakens Rust type inference.
But Tyler, we have overloading. It's just like the version of overloading you'd get if you ordered overloading on wish.com.
What's that?
You know, like, you ask Ferris for overloading, and he's like, we've got overloading at home. But then you get home, and you see this mess. We can emulate the same behaviors as overloading with all the same problems in Rust, if we're willing to be creative. Above, you can see that the Rust compiler is using the types of the arguments to sumfunc in order to figure out which function to call. Also, we all do this today. Anytime you call from on a type with multiple from implementations, the compiler uses the types of the arguments in order to decide which function gets called. The into trait is actually even more powerful. It can use the expected return type to determine which function to call. Adding an overload can break calls to into, But this is also true for functions with generic or impl trait arguments today. Rust should just support built-in overloading, especially for interop with existing languages. Overloading can be much more readable and is no more powerful or confusing than today's trait-based analogs. In addition to allowing us to consume C++ overloaded functions, Rust overloading is a perfect solution to our earlier aliasing problem. Rust code, which has an exclusive mutable reference, is actually able to safely invoke C++ mutation APIs. However, if we have a potentially aliased reference, the C++ API becomes unsafe. This strategy also works for methods.
So as always, we don't want people to get carried away. Type inference makes overloading less of a good idea in Rust APIs than in some other languages. And of course, no one wants to use an API with 17 different overloads for the same method name. But I believe Rust can avoid these issues for the same reason it has gotten away without overloading to date. It simply has more tools in its toolkit, like zero overhead traits and generics and new types, that you can apply in situations where you don't want to accept the trade-offs of overloading, but where you might be forced to in another language. What's really clear is that when it comes to interop, you should be able to call overloaded functions defined in another language without jumping through awkward hoops that aren't well supported and that create a bad developer experience.
Okay, let's all take a moment and breathe together. That was a lot. Creating Rust APIs on top of a complex language like C++ is really difficult. We talked about applying unsafe in a way that will allow us to focus on danger points. We talked about lifetimes, about mutable aliasing, non-memcopy movable values, and overloading. Now, let's talk about calling Rust.
Calling Rust from C++ is much more straightforward. Rust is a simpler language than C++, and its strong type system makes it easy to understand the intended semantics of types and functions.
In fact, my team at Google, the Crubit team, is doing this already today. We automatically generate bindings to hundreds of crates. We're able to accomplish this by using the Rust compiler to analyze a crate's API, looking for all public functions and type definitions. Calling into the Rust compiler itself allows Crubit to determine the exact size and alignment of every Rust type and its fields, as well as trait implementations such as drop, which we can translate into a C++ destructor, operator trait implementations, which we can translate into an overload of the corresponding C++ operator, clone, which becomes a C++ copy constructor, and more. Do note that Rust doesn't offer a stable ABI, so the auto-generated APIs here need to be regenerated when the Rust compiler is updated. In the future, we'd love to see a tool like this, possibly an upstreamed form of this portion of Crubit, make its way into the list of standard Rust components, like cargo, Rust format, or Clippy. One particularly interesting thing about exposing Rust APIs to C++ is that it is actually possible to support C++ usage of generic Rust types. This is possible even though Rust types can have different in-memory representations depending upon the generic parameters. When we see a Rust definition of a generic type such as option, we can declare a corresponding template in C++. We'll use static assert to mark this initial declaration as unusable, though, since we don't actually know the concrete layout of our option. Then, each time we see a usage of option with a new concrete type parameter, we can generate a C++ template specialization with the corresponding type substitution. Note that this means C++ code can't instantiate option with a type until there is a generated Rust binding, which provides a declaration with that particular generic parameter. For example, if C++ wants to use option of some type, there must be bindings to a Rust API which uses option of some type. Until we see a Rust usage site, we won't have generated a specialization of option with that particular generic parameter. This can create friction. If you define a new C++ type and want to store it in a Rust option, you'll have to first declare an intermediate Rust library which uses option of new type somewhere in its public API. Once you've done that, you can create a separate C++ target using the Rust option of your new type. That wasn't so bad, though.
By contrast, C++ templates are much harder to bridge to Rust types. Rust doesn't support specialization, so we can't apply the same trick we just used coming from C++. There are a few other tricks we can use, though. Today, we can generate unique types in Rust for separate instantiations of std tuple, for example. That is, for each unique combination of parameters, like A, B, C, we can generate a new Rust type, like std tuple ABC. Sometimes when passing types by value over the language boundary, we can convert them into a more language idiomatic form. So here, when returning a tuple from C++ to Rust, the automatically generated code unpacks the C++ tuple and repacks the values into a Rust tuple. Note that this only works for types passed by value. C++ tuples and Rust tuples don't have the same in-memory layout, and we can't change the layout of types behind a reference or inside a field of an existing struct. That means conversion-based bridging like this, it can only be used in a handful of places, but it does make for really nice idiomatic APIs. We can also make Rust generic APIs for C++ templates whose representation doesn't depend on the template parameter. So for example, C++'s vector and unique pointer types have representations that are the same no matter the template parameter. In the case of vector, it's 3 pointers. Today, crewbit lets you manually write types like this as bindings for templated types. These approaches work for a lot of situations. But as a final cherry on top of this presentation, let's take a moment to peer way into the future. Consider what it would take to go beyond these strategies and deliver a truly streamlined experience for generics. For that, we'll need an approach that goes beyond source generation. For that, we need compiler integration. Now, compiler integration is not that scary. The basic idea is that you take the insides of one compiler, like rustc, and the insides of a completely different compiler, like Clang, and you make them talk to each other.
That sounds kind of like the premise of a horror movie, actually. Look, you just made Ferris turn into Koro.
OK, but the idea is not as scary as it sounds. In fact, Swift uses compiler integration with Clang to automate bindings to Objective-C and to C++. And we can do this in a principled way through the use of an extension point that goes beyond the core language. So let's imagine our stream template looks like this. One key idea is that when you substitute parameters into a C++ template, that actually works a lot like doing macro expansion. So what if we could have something like a proc macro that got called every time you used stream of t with a new t? That proc macro or plugin could receive type information for your input type. In this case, the compiler would see stream of mything, and so the input type would be mything. Full type and layout information would be available to our plugin, which can execute arbitrary logic to define the layout and API for stream of mything. That could include calling into a C++ compiler, like Clang, to get all the information it needs. There's a lot of architectural work that would need to happen in the Rust compiler and/or in crewbit to make this possible, so we don't know if it'll happen. If it does happen, it could make using templated C++ APIs just as nice as using non-templated APIs.
All right, well, it's about time to wrap up. We've covered a lot. As you can see, the path to seamless C++ Rust interop is complicated, but it's a journey we're committed to. C++ remains the lingua franca of systems programming, so expanding the reach of Rust's memory safety guarantees requires that we have a rock-solid story for interacting with large, existing C++ code bases. We can gracefully meet the needs of all C++ users by providing tools that use a combination of auto-generation and interface definition languages.
I'm excited to see how good of an experience we can create for people migrating from C++ to Rust. One big part of this experience will be new language features. Features like auto-ref, custom field projection, and tooling-supported overloading will improve the experience for all Rust developers, regardless of whether or not they use C++.
Thanks so much for coming to our talk. Please reach out to us if you're also working on or interested in this problem space. There's the conference Discord, or you can come up to me directly or message or email either of us. Thank you all so much.
Thank you.